Hello everybody. Today I'm going to present determination of energetics of organic semiconductors, mostly focus on organic solar cells. One thing is, why is energetics important? Well, your device parameter will depend of your material properties, and one of them is energetics. For example, sorry, let me have a pen. In the case of, for example, PCBM, it has been shown that actually the offset of the electron affinity, we need an offset. Oh, sorry, the light just turned off. It's okay. We have an electron. We need electron affinity offset between the donor and the PCBM in order to have driving force and have a good charge generation in our devices. So it has been determined empirically. Here it's 0.3 in the case of PCBM. But well, organic solar cells have evolved. Now we are mostly using non-ferrous acceptor. And in that case, well, which one? I'm sorry. It's a bit dark. I will just turn on the light. It will take like 5 seconds. I'm really sorry.
Go ahead.
I'm very sorry. So in the case of non-ferrous acceptor, we don't know, well, in this case, what should we have? So in the case of the non-ferrous acceptor, it have been shown that for the electron there is not a charge transfer, there is an energy transfer. So but in the case of the hole, we have a charge transfer. So most of the study are focused on this IE offset. And several papers have actually shown that this offset can be negligible, which means that we can have similar HOMOs for the donor and our NFA, and it will not affect our charge generation. So here we can see that even for those blends, actually we have a good charge generation, even if the offset can be even like negative. So this is probably because of uncertainties, but anyway, like we have like very low offsets, but we still have good charge generation. In another hand, we have like more recent paper that actually are showing that we need IE offset. And like this offset that they determine needs to be above 0.4, well, 0.3, 0.5, like, but we need this offset to have a good charge generation, to have high efficient solar cells. So you can understand that we are in a situation where the several papers are saying opposite stuff, and we can ask ourselves, well, in that case, which one should we follow in order to design new molecules? Should we like try to design molecules with low offset, with higher offset? It's very important to know which like path we should follow. So we decided to dig a bit more into this, and if you look a bit closer about on those two papers, you see that actually in this paper they are using cyclic voltammetry to determine their energetics, where in this paper they are actually using photoelectron spectroscopy. So we decided to dig a bit more into this to determine, okay, well, is it the method? And if it's the method, what should we do? So let me a bit introduce first those two methods. So the cyclic voltammetry setup, it's a well-known setup, quite inexpensive, easy to build, where you have a working electrode, a counter electrodes, a reference electrodes, and all those electrodes are immersed into an electrolyte. on this setup, you will apply a certain voltage and you will gather a current. So the voltage that you apply, you will have a ramp of voltage that you increase at a certain rate and that you decrease. So you will have this cyclic graph here, which each step correspond to a certain environment in the setup. So how with this graph we can extract our energetics? So here it's an example of what we measured. So here it's I just took the Y6, where you see like this peak. In order to extract actually our energetics, we take the onset of this peak. So we have the baseline, we take the tangent of the peak, and you will be able to extract the onset. So here it's around 0.9, 0.89. And after we will use those equation where you will have your HOMO here and your LUMO here. So here it's the constant of the ferrocene versus the vacuum level, since we use the ferrocene as reference. Here it's the oxidation onset that we measure here. And there is also a correction of the ferrocene versus our reference electrode. So with this, we have access to the oxidation energy, which is commonly called HOMO. And in the case of the reduction, you do the reduction, you do the same determination, and then you can have your now the photoelectron spectroscopy. So it's a quite bigger setup compared to the cyclic voltammetry. It's ultra high vacuum setup. And with this setup, we can measure the UPS, so ultraviolet photoelectron spectroscopy, where we send actually photons on our devices. So photons with a very particular energy, which is created with the plasma of helium. And we gather the electrons and we measure the energy. Here you can see the spectra that we measure from this setup. And from this, we can determine two values, which is the work function and the valence band of our material. So to determine the work function, we do the same. We have a baseline, we have a peak, and then we take the tangent of this peak, and then we have the onset, which is our work function. For the valence band, we are actually focusing a bit more in this region, and you will have this shape. In this case, to determine actually the valence band, we are fitting Gaussians in order to access this Gaussian and be able to have the tail of the Gaussian and determine our valence band. In order to have our IE offsets, we just need to add to our work function the valence band that we measure here. Now, for the electron affinity, which is also commonly more commonly named LUMO, we use low energy IPES, so low energy inverse photoelectron spectroscopy, where in that case, we'll send electrons to our sample and we will gather photons. From there, we will have this spectra, and the same as before, we do the Gaussian fitting, and we take the tail of this Gaussian, and then we can have access to directly to our electron affinity. I just want to focus a bit more on the low energy IPES. One setup that is more known is the IPES. However, the IPES, so inverse photoelectron spectroscopy, is higher in energy than the low energy, well, like it is in the name, low energy IPES, where we have like much higher energy. And this is actually a problem for the organic material, because when we use the IPES, we see that over time we have a change in the peak. After a few minutes, we see that actually we are destroying our material. So to measure the electron affinity, directly the electron affinity of our organic material is not possible with the IPES. However, with the low energy IPES, you can see that even after hours, we see like almost no change in the peak. So we have the chance to have the low energy IPS here. So we use this method in order to directly measure the electron affinity of our organic material. Also, it's good to know that with the low energy IPS, we have a better accuracy than the IPS. With the IPS, we can have an accuracy of 0.35. With the low energy one, we'll have an accuracy of around 0.1 EV. So before to continue, I just want to give some some definition that maybe I already talked about. So we have the ionization energy that we measure with the UPS, the electron affinity that we measure with the low energy IPS. We have the LUMO and HOMO, which are the lowest unoccupied molecular orbital, the HOMO, which is the highest occupied molecular orbital of our material, the transport gap, which is the difference between the LUMO and the HOMO, the band gap that we measured, which is an optical band gap, the binding energy. One thing that I forgot to mention about CV is that for most of the donor, one problem that we have is the measurement of the reduction potential. Sometimes we can, most often we we cannot measure the reduction potential. So what is generally done is that we measure the oxidation potential, we measure the band gap, and then we add it, and we say it's the LUMO of our material. But you can see that actually we are missing part of the energy, which is the binding energy of our exciton. Here also we have the PV gap that we will talk a bit later, which is the difference between the HOMO of our donor and the LUMO of our acceptor. And yeah, well, the delta EA, delta IE. Okay, so here is an example of what we measured with the Y6, with the UPS, IPS, the reduction potential, the oxidation potential. We wanted to compare those the measurement that we made. So here you have the example of PM6AY6. Here you have in square dash is the measurement from CV in red, and in black and plain square, it's the photoelectron spectroscopy. And you can see that, well, there is differences. We have big differences, mostly for the PM6. In the case of the Y6, it's still okay. But you can see the confusion where we see actually in the case of the CV that we have a low offset for the IE, but in the case of the PES, we have a larger offset. So in order to study a bit more this, we decided to do this for more materials. We did for 33 materials, 21 acceptor and 12 donors. So the plain square are PES and the dash square are from CV. And you can see that, well, it was not only for the case of PM6Y6, it's actually for all the material, for all the material that we measured. So you can see that, well, there is differences, and well, we need to figure it out. We need to figure out, okay, well, in that case, which one should we use to explain, for example, our device properties, and which one we should use in order to design new molecules. So before to go towards the devices, we tried first to correlate those values to see if there were any, like, if it was just a shift, or if there were like more than this. And like previous paper before us, we see that, well, there is no clear correlation. There is kind of a trend, but it's very scattered. So we cannot like try with CV to predict PES values, like it's very scattered. So this is the case for the donor polymer. It's also the case for the non-ferrous acceptor. It's even worse. Like it's very scattered. So we cannot like just interchange between those two values. We did also DFT calculation, try to correlate also, and again, like correlation, it's not clear. So after we decided to go towards the blends to see which one with which one we could correlate better our measurement. So here you can see we did like with several blends, 8 blends with different donors and different acceptors, and we tried to correlate the VOC that we measured from those blends with the EPV, which is the difference between the HOMO of the donor and the LUMO of the acceptor. We correlate also the VOC estimated at 0 Kelvin. So in order to have those value, what we did is a temperature dependence measurement of the VOC. So we just measure the VOC at different temperature. We decrease the temperature until 200 Kelvin. And after, once we have like kind of a trend, we just extrapolate until 0 Kelvin, and then we have this VOC estimated at 0 Kelvin. And it has been shown that it is an estimation of the CT states. So here we try to correlate for all our methods. So with CV, with photoelectron-spectroscopy and DFT. And we see that in the case of the CV, we don't see clear correlation. We tried to do the plot, but like the R-square was very low. Like, and well, you can see it better with this graph, where you see actually with the PV measured from CV in blue, compared with the star, which is the VOC estimated at 0 Kelvin, there is no trend. Like it's a bit chaotic. Like we don't see any correlation between those two. When we look at the PES, we see a better trend. Well, in the case of the VOC, we see that it's not like clear, but in the case of the VOC estimated at 0 Kelvin, we see that like there is a clear trend, and you can see it with this in this graph, where you see the EPV from PES that clearly follows the VOC estimated at 0 Kelvin. So here it's a first clue about okay, which method we should maybe focus on. But here, to make you feel a bit better how it is like you have like two blends here. So you have the PTB7TH Y16 and PTQ10 Y16. When we measured with CV, you see like there is no offset. Even here, like even top, like for the HOMO offset, LUMO offset, you don't see any offset. Here, same. Like we don't see any offset of the for the HOMO. When we measure with the PS, we actually see an offset for the PTB7TH with Y16, but again, we don't see offset for the PTQ10 Y16. So let's see at IV curve. And when we look at the IV curve of our devices, we see that there is a difference between those two blends. One have some trouble with the charge generation compared to the other one. So the PTQ10 have some trouble for the charge generation, where we have a better charge generation in the case of the PTB7TH. And while we couldn't predict this trend with the CV, because well, with the CV we had like low offset for both. In the case of the PES, we see that actually if you have here an offset, you have a better generation charge generation compared to the one that is have a low offset. So of course we did with more devices, and here, as Professor Lackey's group showed, is that if you have a trend between the delta IE that we measured from the PES with the GSE with the charge generation of your device, which you can see here with the GSE. When you have a low delta IE, you see that you have a low GSE, and like when you have a high GSC, you can see that actually the delta IE is quite large. But this trend, we cannot see it in the case of the CV. In the case of the CV, like you have both blends with low charge generation and high charge generation, where you see like with low offset. So you can see here that actually with this, it's another clue that in the case of the CV, we cannot actually correlate to the device property compared to the PES values. So yes, one thing that is very important is that with the PES value, the low delta IE is detrimental for the device performance. So to conclude this talk, we used the low energy IPS, which is a direct measurement of the organic material, that we see significant differences between the energetic that we measure between PES and cyclic voltammetry. And when we compare those values to the device property, we can see that actually with the PES, we are able to correlate to the device property, which is not the case of the CV. So I would like to thank my group, Professor Daria Baran. Big thanks to Dr. Anirudh Sharma, who contributes a lot to this work. Dr. Jianhua Han, of course, Professor Frédéric Lackey's group with Dr. Julian Goranflo and Dr. Catherine de Castro, and Professor Thomas Antopoulos with Dr. Emre Yeni. Thank you for your attention.